Hey everybody, it's John Buck back with another discrete time linear systems video. And in this video I'm going to show you a couple quick examples of doing the inverse Fourier transform by using the tables or examples we've already seen and the fact that we know the Fourier transform is a one-to-one mapping. So if I've already started with time and found something in frequency, I can use that and possibly properties when I get a new thing in frequency to go backwards in time. So let's see how that works. Again, today's topic is inverse Fourier transform examples. And for the first one, we're going to say, well, suppose I was asked to find what time signal, right, what I'm saying, find the inverse Fourier transform. What I'm really saying is what time signal has this for the Fourier transform. And so I've got 1 over 1 minus 1/3 e to the minus j omega. And this should look familiar because we have already seen the example in the book and earlier examples in class of saying, well, if I have a to the n u of n, then I get, if this were my x of omega, x of n, then e to the j omega would be 1 over 1 minus a e to the minus j omega. And so by looking at this, I say, well, I can just match these up. I say, looking at this, if I set a equal to 1/3, I've got this exactly, so that tells me by the uniqueness of the Fourier transform that x of n up here, I can say there's a Fourier transform relationship here. So using my little script ft notation, that this one will be 1/3 to the n u of n is what my x of n will be equal to. Should have left a little room to write that in the front. Right, so that one is almost mad easy, right? That's silly how easy it is when you can recognize it. But we can get to more complicated places using properties once we learn the properties. So here's one that's a little more complicated. We're saying what signal in time has a Fourier transform that's 4 times e to the minus j omega over 1 minus 1/3 e to the minus j omega. The denominator, we can look at it and say, I've seen that thing before. That's like the example we just finished. That's really close, but we need to be able to unpack what's going on here, and this is where using the properties comes in. We say, well, this is like the one we just did, except it's been scaled by a constant, and it's been multiplied by a complex exponential. But if we think about our properties, we say, well, I know the Fourier transform is linear. If I multiply by a constant in frequency, I multiply by the same constant in time. And I also know this property that if I multiply by a complex exponential in frequency, I'm shifting in time, right? So I can say this multiplication in frequency means a shift in time, and this means a scale in time, right? So looking at this is enough to use the properties. We can say, using those properties we saw, well, we saw just a minute ago, x of n is 1/3 to the n u of n, and that gave us x of e to the j omega was just like this, except the denominator was 1. I'm sorry, the numerator, I misspoke there. The numerator was 1. Well, looking at this, then I can say the scaling, multiplying by 4 in frequency, scales by 4 in time. So I can say this signal, y of n, will be 4 times, and then this multiplied by the shift means a delay when I compare things. This would be like a delay with it by 5 would be what we have right above, y of e to the j omega. Right, so rather than going through a lot of trouble to find these, I can find ways to be a smart, lazy engineer using properties and get it directly like this and say, well, now I can just plug into what I have here. So that would be 4 times 1/3 to the n minus 5, u of n minus 5. It's important to replace both of the n's, including inside the u, when I make this shift, right? I'm shifting the whole signal, not just the exponential without the u. I'm shifting all of it. That's sort of a mistake people make when they start out. So I'm going to highlight it to avoid that. And so this is much easier than starting from scratch or trying to guess this. There are ways to do inverse transforms of this form of these exponentials with an integral, but you have to know some complex analysis. Not required in this class. Any of the ones you have to do, we'll see that in practical signal processing systems, what comes up over and over again are things like delays and these exponential signals. And so if you know these couple properties well, you should be able to solve almost all the ones we're going to see in this class. All right, so that's two examples of using finding inverse Fourier transforms for signals that were exponentials in time and how we recognize them. I'll see you next time at the next video when we talk about maybe a more complicated version of it.